To really figure out what these other surfaces are, we need to learn about something called a trace. And a trace is kind of like just a cross section, a two-dimensional cross section through a surface. And if we can identify what our cross sections look like, we can use those as building blocks to put back together to figure out what the three-dimensional object looks like. So there's two surfaces in space that we know about right now. We know spheres. We talked about spheres back at the very beginning of the semester when we first introduced similarities between 2 dimensions and 3 dimensions. We didn't really do anything with them though. But I think we just very briefly looked at the formula. So that would be the equation for a sphere centered at x sub 0, y sub 0, z sub 0 with a radius of r. If you just cover up the z part, it's the equation of a circle in the plane. So all we had to do was tack on the z piece and all of a sudden it's a three-dimensional sphere. And the other surface in space that we know is the plane, which is ax plus by plus cz equals d. That's our general form. And in this format, the one piece that we could pull out is the normal vector ABC. The d doesn't really have any significance right now. From the standard form, we could see a point that got used to help create it, but the d is a result of all those ABCs getting distributed and combined. So those are two surfaces that we've already seen at some point this semester, two surfaces in space. So the sphere, everything is squared and added together with the same coefficient. The plane, everything is linear and added together. So if we start playing with only squaring some of them or changing some of the additions to subtractions, it's going to change completely what these surfaces look like. Another thing that we said on Tuesday that's going to be helpful is when we started converting, when we were talking about polar coordinates, if we convert and a variable ends up missing from the equation, does anybody remember what that means? If the variable is missing from the equation, if I know something is in the xy plane, but there's no y in the equation, it means there's no restrictions on the y. If I'm told that I have a surface in space, that means it involves x's, y's, and z's. But if one of the variables is missing, that means there's no restrictions on that variable. That means that whatever the object is that's being represented in the two variables, it's going to be repeated forever in the direction of the variable that's missing. And these are called cylinders. What have we learned so far in our life about cylinders? What do you know about cylinders? Anything. Elementary school. Toilet paper. What's the shape of toilet paper? It's got circular cross sections. If you were to like slice it and unfold it, the surface area is like a rectangle. But it's got circular cross sections. It's like a circle that got repeated for a certain amount of distance in another direction. Technically, mathematically, a cylinder can be any shape repeated indefinitely in another direction. So when we first learn about cylinders, we usually talk about circles being repeated. The correct term for the cylinders that we learn in elementary school is a right circular cylinder. Right meaning they stand perfectly up and down. They make a right angle with whatever they're sitting on. Circular meaning their cross sections are circles. So the correct technical math term for the cylinders we learn in elementary school is a right circular cylinder, because there are lots of other types of cylinders. Any shape that gets repeated indefinitely along an axis is considered a cylinder. So this is when a two-dimensional graph gets repeated along the third axis to create a surface. Or I'm going to say along the axis of the third variable. And that third variable is missing from the equation. That third variable is missing from the equation. That's why this graph gets repeated forever in that direction, because there's no restrictions on that variable. So when you first see these equations, they're just going to look like two-dimensional equations. So we have to be told in the instructions that these are three-dimensional surfaces. So in these next few examples, we want to identify and sketch each surface. So even though you're only going to see two variables in the equation, these are surfaces. These are three-dimensional surfaces. Y equals x squared. So let's brainstorm a little bit. What do we know about this? Anything whatsoever. It's a parabola. So let's get a little bit more specific. It is continuous. Go ahead, Arturo. Okay. It has a minimum. It's so facing up is kind of weird in three dimensions. So instead of say facing up, let's say opening in a specific direction. So what direction does it open? Opens in the positive y direction. This is a three-dimensional surface. That was told to us in the instructions. Which variable is missing? Z is missing. What that means is when I draw this parabola in the xy plane, that parabola is going to repeat forever along the z-axis. When we draw it, it's going to look like half a cylinder that's been squished, but technically a parabola goes forever in the y direction, and then this thing's also going to go forever in the z direction. We can't draw forever when we draw, so we're going to have to stop it. The fact that there's a variable missing is what makes this a cylinder. And then the generating curve we said was called what? What two-dimensional graph were we going to draw to help us make this? A parabola. So we're going to come up with some fancy term that puts those together. And it's called a parabolic cylinder. This thing is called a parabolic cylinder. It is a cylinder that is generated out of a parabola. So we've identified the surface. That was one of the things we were asked to do in the instructions, identify the surface. The other thing we were asked to do is sketch it. So we've got our x, y, and z axes. And remember, these are different than how we would draw just the xy axis. So you need to be careful with how you draw your parabola. That's why I wanted us to write down what direction the parabola opened in, because that's important. So we've got a parabola in the xy plane that opens in the positive y direction. So the xy plane is flat, the flat plane, and the parabola opens in the y direction. And since z is missing from the equation, technically z is not restricted. So there's nothing in that equation that's telling me where on the z-axis to draw that parabola. So I can draw it anywhere on the z-axis. So I could also draw it up here. I could also draw it down here. So what ends up happening, I'm going to try to clean this up a little bit. I'm going to make the back ones come out a little bit farther. I have been able to draw this pretty decently in the past. We shall see. And now that I have colors, it should be even better. Is this making it worse? So the blue is kind of the outside coming out at us, and the red is the inside that goes towards the back. And if we slice this thing horizontal, we're seeing parabolas. The shape is a parabola. And there's just an infinite number of them just stacked on top of each other over and over and over again, getting repeated up the z-axis. Because z is missing, that means z has no restrictions, and we can draw it at any z value we want to. So we can't draw it forever, but technically it goes forever. It also goes forever up and down. So these cylinders will always have some two-dimensional kind of graph that helps to generate it, and then it will get repeated forever along the axis of the missing variable. You could also call this thing a cylindrical paraboloid. Y squared over 9 plus z squared over 4 equals 1. What do we know about this thing? Anything whatsoever. Do we know what the shape is? They've got different denominators, which means it's an ellipse. They don't have the same coefficient, which means I'm moving a different number of units in the y direction than I am in the z direction. So it's an ellipse. So Tyler, how did you know that?
Just from having it in previous lessons. Doesn't the hyperbola look similar?
It does. There's one tiny difference in the hyperbola equation. Does anybody know? Has anybody learned about hyperbolas before?
Yeah. Is that a minus?
It's got a minus. So this thing is an ellipse. What plane are we going to draw this ellipse in? The YZ plane. Yes. It's an ellipse in the YZ plane. Which variable is missing? Since we were told it's a surface. X is missing. Which means once we get our two-dimensional ellipse drawn, we are going to repeat it forever in the X direction. Elliptical cylinder. Elliptical cylinder. Cylindrical ellipsoid. So we've got an ellipse in the YZ plane. The YZ plane is facing us. It's like the board. So those numbers underneath the variables are the squares of our radii. So in the Y direction we go 3, in the Z direction we go 2. That two-dimensional ellipse is going to get repeated forever along the x-axis. Right now, I've just got it at x equals 0 on the YZ plane. I could draw it at x equals 1. I could draw it at x equals 5. I could draw it at x equals -3. The x-axis is coming at us. In this class, the x-axis comes at us. I know in physics it's different. So if I draw this out at like x equals 3, it's going to slide out at us at an angle because I've got my x-axis angled. Does anybody know anything that's this shape? So it's like a pipe, but it's not a circle cross-section. It's an ellipse cross-section. So this is one group of surfaces in space. They're cylinders. And when we see their equations, they're a little bit misleading because they only have 2 variables. But we have to be told that there are surfaces so that we know it's not a 2-dimensional graph, it's a 3-dimensional graph, so that we know to take that 2-dimensional graph and repeat it forever along the third axis and make a surface out of it.